Didn't actually make things better, it made things worse. You know what made things worse? By adding this second relationship, I've actually added a third variable. If I didn't know what I1 or I2 was, now I got an I3. So now I've got two relationships, but damn it, I got three of those, not two unknowns. So at this point, we can approach it in one of two ways. I can say, first of all, are these the only loops I really have? How many different ways can you go in a circle and end up where you start?
Well, there's one more.
I can go this way, I can go this way, or I can go this way. That's a loop. Whether or not this is present, it's still a loop. And when I go around it, I got to get back to the same voltage. So it's still a closed loop, even though it's not apparent that it is. And it's because these are parallel and they're attached together like this. Okay? So I've got a third loop. Let me see if this helps. This third loop then would be, over here. This third loop would be this 9 volts going through R1, but also going through now, instead of R2, R3. Whichever path, I can just take a different one, I can define another loop. For this loop, V naught, there's your 9 volts, should be equal to I1, R1, plus I3, R3. I got 3 equations, 3 unknowns. Will this allow me to solve this problem? Yeah.
Can we set that equal to 9 since our...
Oh, yes, and this equals 9. Absolutely. So what's I? If you stare at this long enough, you realize it's only really 2 equations. It's not 3 equations.
Right. 'cause
This equation here
it
forces this equation and this equation to be the same thing, so we still only have 2 equations, 3 unknowns. We actually can't solve it yet. So we have to take another tack. There's something else we have to consider. What can we say about the movement of the charge or the current itself?
that it's equal to a total resistance.
Yeah.
Divided by, or voltage divided by total resistance.
We can play this game. Not helpful here. Actually, we can solve it here if we add one more piece. But before we even get to that piece, let's take a different tack. What is it that we can say from the perspective of, well, let's think about an iPad or an iPod or a phone. My phone again. Okay. Here's my phone. Inside there's a battery at one end, and it's got more than 2 connections, but let's pretend like it has a plus and a minus. And the charge is flowing out of the battery, doing something in this little black box, and then flowing back in the other side. Without knowing any more about what's going on, I could say, if we visualize this circuit as basically the power supply. So there's your 9 volts. And some big-ass black box. I don't necessarily know what it is. I'm going to call this the load, the total load that's drawing the charge out of the battery or out of the power supply. So, in other words, instead of looking at the pieces, let's look at the whole thing. Well, what can I say about this whole thing? Well, you can call this thing R, I don't know, whatever it is, R load, R equivalent, whatever you want to call it, but it's got some combined resistance. I know it has some combined resistance because there's going to be a certain amount of current that's flowing out of this, and that's going to be the same amount of current that's flowing in it. Or, if you will, I got a loop. And this loop tells me that V naught should be equal to I, should be equal to R load. Question then becomes, well, what is this mystical, this mystery resistor? What is this load? This is where all of our discussion of resistivity and conduction comes into play. For the two of you that have probably seen something more eloquent, more detailed than an electric circuit, yes, I could have solved this in 3 minutes, 5 minutes ago, or 20 minutes ago. But it's very important that you understand what's going on, because as the problem scales, it's a lot easier to approach if you can see the pieces. So, what do we know about our load? Well, here's what I can say about our load. Whatever this thing is, this is the equivalent of this. Fair enough? This is the black box that all of this stuff is in.
Is this where we calculate them in parallel and
Series, yes. So at this point we say, okay, well, what is it that I know about how resistances are related? And you put resistors side by side, any kind. It's like taking a conductor and slicing it in some way so that you have two pieces independently that are each part of the total pathway from one side to the other. So across this region here, and we actually evaluated this, what I can say is between these two, I could treat that as an equivalent R2, R3. This is a parallel connection, and I can treat them as some sort of a equivalent parallel branch. And we've already looked at that. Well, what is R2, R3? We'll note that R2, R3 is related because we have a parallel connection. It's related this way. Which in this case allows us to say, since they have the same value, I'm just going to cut to the chase and say that this implies that the combination of R2, 3 will be 50 ohms. Two equal pathways mean you double the capacity, all things being equal. So, making that one little logic step allows me to say, oh, this branch here, this combination, these two branches together in parallel, they're connected by VN. Which, by the way, means that there are two elements that have the same identifiable potential difference across them. Same plus, same minus on either. Connected plus and minus. That's how you define, it's another way of defining a parallel connection. Now we have a similar situation to what we had before. The only difference is it's a 50 ohm resistance combined with a 100 ohm resistance. Well, if I take this tact, I can do one of two things. I can do another equivalent resistance Or I can just go right to the chase and say, okay, once I've got this, now I've got a single loop circuit that looks just like my original loop circuit over here, right? So I'm going to erase this stuff and say, oh, you can write it down in further steps. I can't because I'm running out of space. So I'm going to make note that that circuit reduces now to R1, and then here's my R2-3 combination. The advantage of this is now I can say, oh, whatever current is flowing in, that's going to be the current flowing through R1 now. It's also going to be the combined current flowing through I2-3 together. So the solution is the same solution we did previously. In other words, now if I look around the loop, I can say that, oh, V naught, which is equal to I times R1, and that's I1, R1, plus I2-3 times this R2-3 combination is equal to 9 volts. So I wanted to calculate I. I would take the 9 volts, and similarly to what I did before, I will divide it by R2 plus the R2-3 parallel combination. And now I have 9 volts divided by 150, which is larger than the previous example, 9 volts divided by 200. And that number turns out to be larger than 0.045, I know that.
What is it?
So adding the connection, it's addition by subtraction, in a sense. Adding the extra drag, if you will, adding the extra resistor, actually lowers the total resistance. How much so? Previously, I was driving 45 milliamps. Now I'm driving 60 or drawing 60 milliamps of current out of my power supply. So my R load then is basically the ratio of voltage to current, or 9 volts divided by 0.06 ohms. And that number, well, you could calculate over here. I guess I should have just did that. That's 150. Amperes. Volts per ampere ohm. So there's 3 or 4 different ways that are equivalent ways of looking at this. And the key is to sort of see different ways. That's where the Zen comes in, because when a problem scales up a little bit beyond the ability to look at it in simple pieces, then we have to sort of massage ways around it to take the most efficient solution process, which is kind of like jazz improvisation, if you will. You got the blues scale and how you piece it together to make something happen. It just comes a little bit with practice and feel. And so let's take a break. I'll summarize what we've done here, and then we'll apply it in various ways. But this is the foundation for every other electric circuit you ever deal with.
Yeah, yeah. Right, I got it. Let's go.
Test next week is the 24th of December.
26, 27, it's all the same thing, right?
You should put this stuff on the next exam.
I think it makes more sense to put it on the next exam than pile, because it's so similar to what we've been doing up through chapter 26 anyway. If you don't, here's the alternative.
No, what I mean is on this coming exam.
That's what I mean. If you don't do it that way, now you add parallel equivalent type circuit problems onto magnetism and electromagnetism, which is unto itself will be its own fun in the sun, so to speak. So I don't care. You'll probably see a little bit of this stuff on both exams anyway, just because I don't think I would pile on too much when we haven't had very much practice with it. But yeah, you'll see some of this stuff. So let's look at some different examples of this. What happens when you have two power supplies?
I don't know.
Let's do two power supplies and just see what happens.
Yay.
So, without changing anything else with the process, have two power sources. And maybe the circuit now looks something like, call this 3 volts. And I'm going to attach it to some resistor R1, and let's make it 10 ohms. And then I'm going to attach that to a second power supply that is, say, 2 volts. Just keep it simple first. And I'll ask the question, well, how much current flows through R1? Yeah, so plus, minus, this one's higher than this one, I'll assume that it's going to flow this way. Because if this is negative, this is positive, negative, positive. If these two are the same point, this potential is going to be higher than this potential, meaning that the voltage is going to be higher here than there. Not always obvious, but I can make this assumption in this case. So, how would we solve it? Easiest approach would be to a simple loop rule. In which case I can say 3 volts up, we go from minus to plus. Now I got a drop here. So 3 volts up will be equal to I times R1 plus 2 volts. Voltage rises equal to voltage drops. Or alternatively, 3 volts minus IR1 minus 2 volts equals 0. Either way, I'm just applying a loop rule. Yes?
My question is about the orientation of the batteries and the positive and negative ends of them.
Uh-huh.
I'm not sure I understand why they're oriented the way they are.
I just plugged them in that way. Plug them in any other way.
I mean, it looks to me like you've got positive flowing into positive and negative flowing into negative.
Yeah. Don't get lost in what absolutes have to be. What has to happen is charge is only going to flow from its highest potential to its lowest potential, period. Now, the reality is, if this were a battery where that's not possible, in other words, it does not have any reversibility at all to the chemical process or whatever that's inside, then it's basically an open circuit and nothing will flow, and it might as well be open. But for any form of ideal power supply, which is more or less what we're dealing with, in other words, even though we say it's a potential rise, the assumption is a charge will flow based on the direction of the electric potential difference, regardless.
If that battery was turned around, would it not then change the,
Oh, it'd change everything. And we can look at it that direction, too.
would you?
Yeah.
Let's do this one first.
Okay.
So, what is the current that flows through this thing, and what can we say about it? The intuition should immediately say that if they have the same common point here, and you jump 2 volts here, and you jump 3 volts here, then this side is 1 volt higher than this side, and so the potential difference that's going to push the current across is only going to be 1 volt. So having these two together kind of cancel each other out. So, if I were to draw this, I could say, oh, look at that. If I start from the bottom, I go up 3 volts on this side, and I go up 2 volts on this side. The difference between this and this is this resistor. Because they're both connected at the bottom. It's like starting here, and if I went up 2 parallel paths up Mount Hood, when I reach the campsite on this side, I end up being 1 volt higher than when I reach the campsite on this side. So I'm on opposite sides of the mountain, not at the same spot. That will define the potential difference across here. So I just thought about it, probably this is the simplest way, up here or here, either way. Then I can say, oh look, if I solve for I, it's going to be the difference between 3 volts and 2 volts, or basically what I said anyway. And then if I divide that by that resistor, that will be the charge that flows through that region or across that element. The key is just, however you choose to look at it, if I start here, I just note that I'm rising, I'm falling, and as I go from positive to negative, even though it looks backwards because it's a battery, I'm still dropping. The only thing I can say with certainty is when I come back here, I'm exactly where I started. There's no way around it.
This is an example, if you jump a car, right?
Yeah, oh, absolutely. Jumping a car battery. Your battery drops, the resistor in that case is actually the internal resistance inside the battery as the battery depletes. Now, chemically, there's a reason for that. I won't get into that. But ultimately, it drops the voltage output when you try to draw large amounts of current out of the battery. Net result, it won't charge. I'm sorry, it won't drive the starter. So in order to get the car to start, you hook up a battery with the voltage it's supposed to be. And in turn, that voltage, since that power is high, or that voltage potential difference is higher when they're grounded to the same negative spot, it will force current into the battery. And if you get enough in there, then this will rise to 3 volts, and then you can run it again. So, very much so. Or any recharge process works this way. So you charge your battery, you plug it into the wall socket, 2 volts, but because of this sucker here, now there's a little subtleties here because there's typically an associated resistance. We'll get to that in any power supply. Nothing is ideal. You can only draw so much energy. Well, why can you draw so much energy? 2 reasons. One is that you have any chemical reaction, there's always a limit to how fast it's going to run. And that limit of reaction will depend, among other things, on the quantity of the substrates involved. The more reactants you have, the higher the probability they'll chemically react, the faster you'll get product form and electrons out. When you deplete your quantities, you really are spacing out the chemicals that are reacting, and you're slowing down the reaction process itself, which limits the amount of current that you can draw out, which looks effectively like a resistance inside the battery. We're not quite to that point yet, but that is sort of what we're going to be building to next. Yes?
How would Paul and Jane if the power supplies were in series as discussed?
Well, let's look at it. First of all, let's now,
They are in series.
by the way, when you have a connection like this, there's absolutely no reason why you have to put this R up here because of the nature of the connections, and it's one continuous path anyway. You can put it down there, and now you've got the power supplies in series and resistors outside of that. Okay, so it doesn't matter. You can, when you know you have a series circuit, all the elements are interchangeable as long as the orientation of your power supply stays the same. And that makes it helpful for visualization sometimes. if nothing else, just visualize it, makes it easier to look at. So, after a long wait, let's flip one of these and see what happens now. Now I'm gonna flip this.
See it now that you used your little campers on the hill. You know, like you-
Now I'm gonna do it this way. I don't care where I put this, I'll put it back up here. Make it a lot easier, okay? Now, here's what happens now. Again, absolutes are meaningless. It's the differences that drive the workflow or the energy process, the energy transformation, charge flow. So, anytime you set two batteries, even though this is a positive end and this is a negative end, anytime you set two of anything in the same connection, it forces these, or it establishes the same electric potential between them. So, instead of, if this is 0 volts, normally we think about it this way, and this is just to give you a sense. We normally say, oh, this is 0 volts, and this is, say, plus 3 volts. And then we'll say this other one is 0 volts and 2 volts, right? Well, all these volt values do is define the difference between the endpoints. So if I plug this into here, that doesn't make this, all of a sudden, it doesn't violate any rule. By plugging that in here, all I do is establish if this happened to be, if for some reason we could say that with absolute certainty this is 0, then this is -2. It's just 2 volts below. But it doesn't matter. Well, we never talk about the absolutes, and that's why at some point you just start calling things V, because it never really matters what 0 is. It's just the voltage across something. So, using that approach, come back over here and look at this circuit now. Well, now I can say if I start here, what happens? I go up 3 volts as I go around, then drop 3 volts. How do I know I dropped 3 volts? Because I know it's lower here
If you go up
than
3
it is
volts-
there.
If you go up 3 volts from wherever
I'm
you
just
started,
starting right here.
but isn't there 2 volts there? So
No,
wouldn't it
there
be
is
5?
not. That's what I was just saying. There's not 2 volts here. If I'm calling this 0, I'm calling this my floor, that just means that this is 2 volts below that.
Oh, okay.
So I've either got one of two things. Since everything is relative anyway, here's what I might do, and this sort of gets around that conceptually. We've been starting our circuit here. Let's not start it there. Let's call this my start point now. So if this is my start point, going from here to here, I'm going up a hill. So I add my 2 volts now. I start here, if this is where I'm starting, I go up 2 volts. I get here. Now I go up 2 more, or 3 more volts. So now I'm up to 5 volts. Then whatever it is I do, the only thing I have in between them is R, and the only thing I can say for certain is when I get back here, I gotta be back here, so this has to drop regardless in order to get back to my starting point. Whatever this V is, the drop has to be equal to the rise. So this is like going from the basement of Macy's to the 2nd floor. So you go up the one escalator, go around the corner, go up the 2nd escalator. Now you're up on top, but to get back down, oh hell with it, I'm going to take the elevator. Just go back down. Either way, when you get back to where you started, you're at the same voltage again. Okay, that always has to be your compass north. Because no matter what, when you go around a complete loop, when you end up where you start, whatever that voltage was as you define it, or if it's up here, if you end up there, whether you're going this starting and going this way, or whether you're coming back around and going this way, it's the same right there. So, to set up the problem then, however we want to look at it, maybe we do something like this. I start here, I'm just going to work around, even though I'm going down vertically as a diagram. And by the way, when in doubt, draw it out in a way that's easier to visualize. So I'm just gonna rearrange this and tip things over. This is the same circuit without anything changing. If I just slide it over without doing anything else, I can say, oh, there's my 2-volt battery. There's my 3-volt battery. There's my arm. Oh, I didn't rotate it, didn't change anything. Now it's easier to see if I start there, which was over here. I'm going up 2, I'm going up 3 more, and then I gotta drop that amount and go from here to there. Without changing anything, just how you visualize it, like a free body diagram, will sometimes make your life a lot easier. Key is to see where you can do that. Not always easy, but when you can do that, life is good. So, either way, if I apply this little loop relationship, I have a rise of 2 volts plus a rise of 3 volts going to be equal to my current times my resistance, because that's where the drop is going to come, that's where the work is performed, that's where I lose potential instead of gain potential. Energy in, energy out. So the current then would be 5 volts divided by whatever that resistance. Did I even give a value for that, R?
I did, it was
It
the
was.
same.
Yeah, it was 10.
It was 10 ohms.
Okay, so it's 0.5 amperes, before it was
0.1 ampere.
0.1 ampere. So now we can think about some things. When you put your batteries in a flashlight, typically, how do you orient them?
In series. Negative, positive.
In a flashlight, okay?
Yeah,
So,
they're,
Oh, yeah, they're
here's
all
my
like that.
flashlight.
Yeah, yeah.
How do you put the batteries in? Here's a little spring. You typically put them in like this. Minus, plus. You stack them, minus, plus. And then on the top here, you have that little nipple metal piece there that does the positive end.
Yeah.
Why do you do that? What does this look like? And then, of course, what does the current do? Well, on the positive end, it pushes current through the filament, and probably should give myself some more space. On the negative end, then, it just connects to the negative end of the battery. So this is functionally, should do another color. This is what the wire looks like inside.